Good morning, everybody. This is Nicholas Barras, continuing on statistical computing and machine learning. So today we will try to complete the lecture on regularized least square solutions to a regression problem. And in passing, we will see some other forms of regularization beyond the one that we discussed in the previous lecture. So let's see, the topics we will cover today will be regression, but also, as I mentioned, we will see things like lasso regression that leads to sparse solutions. We will see how to address multi-output regression problems. If you recall, everything we covered in the previous lecture, the output was a scalar, real number. So now we will see if we have a vector output of real numbers. How do we deal with that? I want to briefly remind you the geometry of least squares. Basically, these are ideas from linear algebra, but I think will be useful to visit them in terms of these phi vectors that we discussed in the last lecture based on the design matrix capital Phi. And finally, I want to say a few words about a special computation that you need to do with regard to the bias parameter. In particularly, I want to emphasize, so I don't forget about this, that the bias parameter should not be regularized. So it is not responsible for overfitting. So it has to be treated a little bit differently than the other parameters W in your regression model. And of course, I'm going to discuss in closing some other pre-processing steps that you have to do in all regression models. As a matter of fact, in most, I will say, machine learning tasks. And that has to do with centering data. So we will see how this computation of the bias parameter and centering your data can be addressed in the context of our regression models. Okay, so the goals for today's lecture will be to understand regularization and why it is important in regression models, and become familiar with ridge regression, that in many ways is sort of the default method, least squares method for solving this type of problems. Understand the geometry of least squares. Understand how to address multi-output regression problems, and of course discuss these pre-processing steps that you have to do in all your in all your implementations of regression problems. Okay, so let me just remind you the modified or augmented loss function that we have seen in the previous lecture. That involved a data term. So we wanted our regression function to match the target values in our training data set. And then we added the regularization term. And things look like what you see in this equation. The regularization term basically was the L2 norm square of W, and lambda is what we call the regularization parameter. Okay? Now, if you take derivatives of this with respect to W, and I'm not going to do it because it's exactly, we know how to handle this term, and you know the derivative of this is going to be lambda times W. So if you take derivatives, you set them equal to 0, and you solve for W, this is the regularized least square solution that you get. So W is the inverse of lambda I plus phi transpose phi inverse times phi transpose T. And again, we can see that the only difference from standard least squares is adding this constant lambda in the matrix phi transpose phi. And this goes back to what I was telling you in the previous lecture, that in principle this matrix phi transpose phi may be ill-posed, and effectively regularization what does is it improves the conditioning number of this matrix, so you can actually invert it and find a solution W. Okay? What you actually see with this equation W, it is really fits in the umbrella of what is called ridge regression. So when you hear ridge regression, literally it implies a solution for W of this form, and it implies a regularization that looks exactly like what we have here with a quadratic L2 type of penalization. Okay, So that's our regularized solution, and we already discussed that lambda is effectively the parameter that controls the complexity of the model. Effectively, what we have is the regularization selects an effective number of parameters, all right, selects an effective number of parameters that in principle, try to minimize the error that you do in the training data set, but at the same time, try to control the complexity of the model to avoid overfitting. Okay, so effectively, you can actually see that what lambda does is it selects how many non-zero W's you're going to get in your model. Okay, so effectively, not all W's, if you have, let's say, a situation where you have more coefficients W's than data, you don't expect the data to be able to provide you an answer for what these W's are. So the data will only be able to figure out the effective parameters, okay? And that's what regularization is going to help you to do. So regularization is basically the main variable here that controls the effective model complexity. Okay, and so let me discuss a few more types of regularization beyond the quadratic regularizer that we have seen in Ridge regression. And in particular, what I'm going to do is I'm going to take a regularization term that has these absolute values of the coefficients to some power q. So obviously, if q equal to 2, you get these nice contours. These are the contours only of the regularization term, so you get these nice circles. Now, if q equal to 1, you get these squares with the coordinates that you see here, and this is what we call the Lasso regularizer. If q is greater than 1, you get some contours of the regularizer that look like this. Now, we already have discussed more or less about this quadratic regularizer. We would like to see what is the relevance actually of the other type of regularizations. In particularly, we would like to learn something in the lecture today about q equal to 1, which corresponds to what's called Lasso regularization. Okay, by the way, it's called Lasso regularization because this L1 type of component within the loss function is a famous algorithm that goes with the name Lasso that you will learn in the advanced machine learning course when you discuss about sparsity and models that lead to sparsity. Okay, so let me try to discuss a little bit the difference of this q equal to 1, this Lasso regularizer, versus the quadratic regularizer that we have seen in Ridge regression. Now, before I do any discussion on the comparison of these two regularizers, let me just say that I am going to change a little bit the setting of the regularization problem. So if you remember, if I can go back on our previous slide, what we have is we have this we try to basically minimize the error that we do in the training data set plus this regularization term. So what actually I'm going to use is the fact that I'm going to prove momentarily that effectively to minimize this error, it is the same as minimizing the error that you do in the training data set, but with a constraint, and the constraint that you have is it is given by this form. I am not going to prove it in doing the discussion in the slide, but this constraint for a quadratic regularizer for a given eta, and I'm not telling you what eta is going to be, but for a given eta, you are supposed to be inside the circle, and here for a given eta, you're supposed to be inside the square. So you want to minimize the error that you do in the training data set, okay? And I remind you the contours of that error function, that also resulted from a Gaussian likelihood are circles. So you want to find a point on this circle that at the same time satisfies the constraints either for the quadratic regularizer or for this Lasso regularizer. Now, pictorially, what I'm doing here is I'm showing you this for two random variables, W1 and W2, and here is the optimal solution, W star, that minimizes the error that you do in your training set, but at the same time satisfies the constraint that says that you have to be inside the circle that is defined by this number eta. Now, I can tell you, in case you're interested, we will see on the next slide that it, of course, will be a function of the regularization parameter lambda, and we will formally see how we can come up with some calculation of eta. But for now, it's fixed, and this is the optimal solution. Now, if you look at the Lasso situation, because of these sharp corners of the contours of the regularizer, the optimal solution is going to be in a corner. And this is very essential. And why it is essential? Because in a corner, you notice in this particular plot in the space of W1 and W2, W1 is equal to 0. And this is exactly why this Lasso regularizer leads to sparsity in your model. It enforces basically that some of these W's are going to come to be 0. In this particular case with quadratic regularizer, both W1 and W2 are, as you can see, they are non-zero. So the Lasso regularizer leads to sparsity, and that is very good, right? So, and as I mentioned before, sparsity means that the model controls its complexity through this regularizer by forcing some of the W's to actually become 0, okay? And effectively only managing to compute the other W's from your data. Okay, so let me try to discuss how this type of constraint it turns out to be equivalent to minimizing the augmented function with the error we do in the training data set plus the regularization term that we started with. So let me take that I'm going to start with some constraint of this form, okay? And so that's my the constraint that I want to impose, okay? And so now I want to minimize the error that I do in the data, but also with this constraint in mind. So the way to impose this constraint is to actually minimize the Lagrangian function that involves this error function. This is the error that you do in the training data, plus a Lagrange multiplier times this constraint. Okay? Now, to be able to optimize this Lagrangian function, you have to satisfy what's called the Kent-Tucker optimality conditions. And we will see what those are in the next slide, just for your information only. But think that in being able to solve this problem, you're going to have to actually optimize it with respect both to W and to lambda. Okay, so as a first step, you're going to have to take derivatives with respect to W and set those equal to 0. All right, so let's do that. If you take derivatives with respect to W and set those equal to 0, you notice the only dependency on W come here and come on this first term here. Okay, so effectively, this is what leads, all right, so the dependencies on W, all right, require minimizing this, okay, and minimizing this is the same as the regularized least squares problem that we have seen in the, a few slides ago. This is what we call the ridge regression problem for Q equal to 2, but for Q equal to 1 can be the Lasso regression, or you can have any other Q there. Okay, so let's do the following. Suppose that you solve this regularization, this regularized least squares problem, and for a given for a given lambda, you compute the optimal least square solution, which I call here W star of lambda. Okay, so for a particular regularization parameter, you compute you find the solution of this regularized least squares problem, and let's call the solution W star of lambda. Of course, I already told you what the solution will be for q equal to 2, but for q equal to 1, you're going to have to wait to take an advanced machine learning course to see how the Lasso regularization proceeds when it comes to the optimization process. Okay, now if I go back to the Lagrangian function, what you need to also satisfy, the fact that lambda times the constraint has to be equal to 0. This is one of what's called the Ken-Tucker conditions. So in this particular case, the constraint has to be satisfied, so eta has to be equal to this summation, where my W here is the optimal W that I calculated from the regularized least squares problem solution. Okay? So effectively, now what you see is the two problems. The problem that I started working in, if I can go back on this schematic, where I told you that the regularization problem is the same as minimizing the error on my training data plus satisfying the constraint that I'm inside this domain. You now notice that for this particular selection of the parameter eta that you see on the bottom of the slide, then the two approaches are the same. So what I told you before, it's equivalent to our original regularized least squares problem. So for those who are interested to see the general conditions for constraint optimization, I summarized them on this slide, and I mainly am discussing the minimization problem of a function with a positive constraint, or g of x being greater or equal to 0. So you have to be very careful with the signs that you use. So for example, the constraint here is greater or equal to 0, and you can see the augmented Lagrangian has minus lambda times g of x. In our previous slide, the constraint was less or equal to 0, so we got plus lambda the constraint, but here we have minus lambda the constraint. And then we see the Ken-Tucker conditions. The lambda is greater or equal to 0. The constraint has to be greater or equal to 0, and then lambda times g equal to 0. So either the Lagrange multiplier is 0, or you are on the boundary of your constraint, g of x equal to 0. And in our case, lambda is greater than 0, because this is how we control overfitting. So the constraint g of x has to be equal to 0. And that's how, if I can go again back on this slide, this is why this constraint has to be equal to 0. And then it turns out that this value of theta that we used in the previous slide is given by this nice expression where W star is the regularized least square solutions that we obtained for a particular lambda. Okay, so for that lambda and using W star, we define what that eta is that specify the constraint that we saw in this geometric representation of our regularization problem. Okay. So it's nice. So we talked about L2, or this square regularizer, but also we talked about the Lasso regularizer that leads to sparsity. So because of these corners, it enforces sum. Many times, lots of the parameters W to become effectively 0, and that way the model brings sparsity and controls the complexity regardless of what the size of your data set is. Okay, let me keep moving, and one of the things I want to tell you is how to actually do multi-output regression problems. So let's say that your target is not just a scalar, but is actually a vector. So not to confuse the notation on this slide with what we have seen before, usually when you see T bold, okay, it implies your whole training data set. Here I use T bold to define the target which is a multi-output target. So the target here is a vector, okay? So what you see on this slide is the likelihood for a given x. This is my target, okay? And I take it as before to be a Gaussian. The only difference from what I had before, instead of having a vector W transpose phi, which is a scalar as the mean value, now the mean value is a vector, and so this capital W is a matrix. So I keep the precision beta as a scalar exactly as I had before. We will modify this shortly, but W is one of the main unknowns. It's a matrix M by K. So you can see here W transpose times phi then will be K times M by M. So it will be a vector of size K. So here the idea is that my output is a vector of size K. All right. So how do you go about training and computing the matrix W and beta? You do exactly what we have done before for a single output. So you have your training data set. The only difference now is that your training responses, they're not anymore just a vector, but they are this matrix capital T that includes T1, T2, Tn. So for each of your training vectors, the output is a k-dimensional vector. So what you will need to do is you will need to write your log likelihood and then use everything you learned about differentiation and take derivatives of this with respect to the matrix W and take derivatives with respect to beta. So if you take derivatives with respect to W, this is the wonderful result that you get. It does look exactly like what we did before with, least squares. The only difference, of course, is now that we don't compute just a vector, but a matrix of size M times K. So this is a matrix M by M. This is MM by N matrix. So you can actually see that the dimensions match, and you do get a matrix of size M times K. Now you can, notice something very interesting, that if you take the K component of this W matrix and you take the K component of your target labels in this matrix capital T, you actually get that the K component, K column of W looks like this. So effectively, if you look at each column of W and the corresponding column of T, you notice they are connected directly with what we have seen for a single output least squares problem. So effectively, the idea here is that even though we have these K outputs, they're actually the computation, this least squares computation, makes them to be independent of each other. So effectively, what we have is we have a capital K decoupled regression problems that each of them can be solved with the same design matrix capital Phi. All right, so once you compute this matrix, you actually have solved all of these problems, because multiplying with the corresponding target, then you can get the corresponding W. Now, you may wonder, is this decoupling induced from the fact, if I can go back, so you notice that we decoupled them, but we took that the precision here is defined only by a scalar beta. So we have this isotropic covariance. So somebody may wonder, maybe if we use a full covariance matrix, maybe things will be different. Maybe we will get some coupling of these K least squares problems. So you can try this. And here is what I have here. I have this situation where my covariance matrix is unknown. It is sigma. So now you're going to have to take the log likelihood and differentiate with respect to both W and sigma. Actually, the optimization of the log likelihood with respect to sigma is exactly the way that we computed the MLE estimate for the covariance of a multivariate Gaussian. It is exactly the same problem. So effectively, if it's exactly the same problem, I can write down that my my covariance matrix sigma is given by my sample covariance that you see on the bottom, okay? And again, notice that the mean here is defined by my regression functions. And as it comes to the calculation for W, suddenly we see the answer is exactly as before. There is no coupling between the individual, these K regression problems. So somehow, if you are going to couple these problems, you need to do something more than what you have seen in the last few slides. So we're not going to discuss this further, but maybe this is a good sort of mini project that one of you may want to investigate on how to get these coupled regression problems by using a different sort of a likelihood model. Okay, let me just say a few words about the geometry of least squares, all right? And I know this may sound too basic for a machine learning course, but since we have spent already 2 lectures talking about least squares problems, I think it only makes sense to review these things. So remember that what we have is we have this target vector on my training data set that is of dimension n. And I'm looking again on the scalar target, okay? So the vector t is of dimension n. And then we had these calligraphic vectors phi0, phi1, phi mu, and minus 1. Each of them corresponds to each of the columns of the design matrix phi. And effectively, the way that you can geometrically look for least squares is you're looking for a point in the space that is spanned by these vectors phi0, phi1, phi mu minus 1, so that a combination of this vector, right, minimizes the error between your target vector t and this approximation that you do by taking linear combination of these vectors phi0 to phi m minus 1. And geometrically, if you want to find a point on the subspace that is spanned by these vectors phi0 to phi mu minus 1, then the optimal solution is nothing else but the projection of t in that subspace, okay? And that's what the geometric interpretation of least squares is. We're trying to find a combination of these vectors, okay? The vector W defines what that combination is, but we try to find a combination so that the error that we are committing, okay, and when we do the projection is as minimal as possible. Now, the error that you're committing is really nothing else but t minus phi w, right? And you see the error here indicated with this black vector. So you want this, you want this error to be minimal, and the projection, if you notice, if this is a projection, it implies that this black vector is orthogonal to each of these vectors that define the subspace S that you see here. So this vector t minus phi w is orthogonal to calligraphic phi1, to calligraphic phi2, etc. And actually, when you put this in mathematics, all right, so you have the error t minus phi w, and when you take this orthogonal to each of the vectors phi0, phi1, phi m minus 1, and you put all of them together, effectively the orthogonality leads, with each of these vectors, leads to this simple relation that you see here, phi transpose t minus phi w equal to 0. And you can see the reason for that is, right, this error, if you take this row of phi transpose, you're going to have phi 0 transpose times this equal to 0. So the error is orthogonal to phi 0. If you take the second row, phi 1 transpose times this error is equal to 0, etc., etc. Okay? And you look at this equation and you immediately say, I know what this equation is. This equation is my least squares problem, okay? And that's the geometric interpretation of least squares. So the geometric interpretation, the solution that you're computing, it's an approximation of T in the subspace that is spanned by the columns of the design matrix phi. So effectively, the optimal solution, it is the projection of T, that's the projection Y, it's this blue vector on the subspace S spanned by the vectors phi1, phi2, etc. And again, pay attention, these vectors are the n-dimensional vectors. They are the columns of the design matrix, and not to be confused with the vectors that correspond to the rows of the design matrix, that they are of dimension equal to the number of the W's that you have in your problem, or the number of basis functions that you have in your problem. Okay, let me discuss now a little bit these pre-processing steps that I mentioned. They may be very essential to not just to regression problems, but to practically every other task in machine learning. So if you remember, W0 is a bias parameter, and it turns out that W0 is not responsible for overfitting. And if it is not responsible for the overfitting, what we need to do is we need to be careful not to regularize W0. So the only way to do this in a nice way, so we don't get messy equations, is somehow to do some special things when it comes to W0. And the first thing we can do is, can we optimize this error function that you see on the top directly in terms of W0? And what I have done here is nothing else but basically split my regression function to a term that is the bias term, and then all the other terms together. So you notice my summations here starts from j equal to 1. So if you take derivatives with respect to W0, it's a straightforward process, and you rearrange your equation and you define a few new quantities, it turns out that W0 is T bar minus the summation of Wj times phi bar j. So what is T bar? You can see from here is the average of your target values, right? This is the average of your target values. And then you notice here you have phi j bar that involves the average of phi j evaluated at all of your training data. Okay? So effectively, this is the discrepancy between the average target value and what the regression model tells you using the averages of the basis functions over all the training data. So effectively looking at this equation, you immediately say, well, you know what? If I can somehow compute the rest of the W's, I can come back on this equation and compute W0. So the question is, can we actually compute the rest of the W's? Can we compute W1, W2, etc. on their own, and then come back in this equation and compute W0? Now, to do this, somehow we're going to have to pose a new optimization problem that only involves W1, W2, etc. So we will need to do something with W0, and that something is we will need to marginalize and integrate W0 out. So let's see how maybe we can start thinking of doing this. So what I'm going to do is I am going to define, when you see the design matrix phi from now on, like you see on the top equation, this design matrix phi involves all my terms that I had before except the bias term. And you remember when you include the bias term in the design matrix, the first column is really a column of ones. So the matrix phi that you see there doesn't have that. And W here is W1, W2, Wm minus 1, or Wm, whatever you have. So what I have done here, I pulled the bias term outside, okay, because in my original likelihood model, right, in my regression function, I need to have all the terms. So now I called W0 here, I call it mu, okay. just to be consistent with the notation used in Chris Bishop's book. So I call W0 equal to mu, nothing fancy, but this matrix phi that you see there, it only involves the basis functions phi1 to phi m minus 1. It does not involve anything from the bias term. Now, I'm actually going to do something else. That matrix phi that you see there, I am going to center that matrix. And centering that matrix means if you take the sum of every of the elements in every column, that sum turns out to be 0. So I'm going to assume that this matrix phi satisfies this constraint. And it's very easy to accomplish this, right? If you take your original phi matrix that is not centered, you can go through every column, compute the average of every column, and then subtract every element in that column, subtract from that the average of that column. Once you do that, you can immediately verify, right, that you are going to be satisfying this constraint. So this phi that you see here, it is essential for the derivation I am going to do in the next slide or two. It is essential that that matrix phi has been centered. Okay? So again, two important steps. One, we split the bias term and we have it separately, and this phi matrix does not involve the bias term. And then in addition, we center that phi matrix so that it satisfies that the sum of every column turns out to be 0. Okay? All right. Now, I mentioned that to be able to compute W1 to W2 to Wm minus 1, we're going to get rid of W0 by integrating out, okay? And our W0 here is the same as mu. So the way we're going to do this, we're going to put effectively an improper prior, a uniform prior on mu. So we'll take that this prior is equal to 1, and we're going to integrate it out, okay, as indicated in this equation. So the result, this W here will only involve W1, W2, etc. Okay? So somehow we're going to have to perform this very nasty integration. And let me explain. This equation is exactly the same as before. The only thing I have done is I took the average of my labels on my training data set. So this is t bar times the vector of 1s. I subtract it here and I add it there, so I have done nothing new. And then I am calling this quantity A, okay? So effectively what I have is, I'm going to have A minus this transpose times A minus that, okay? So if you take, you expand this inner product of these two vectors, you're going to get a quadratic term in mu, so mu minus t bar squared. Then you're going to get a linear term in mu, and then you're going to get a quadratic term in A. Now, it turns out, and you can guess this immediately by closing the square, this quadratic term in mu will give you the exponential of a Gaussian, okay? And when you integrate that thing out, you will get the normalization factor of a Gaussian, which we don't care what it is. So mu disappears. It will become a constant. And then, interestingly enough, by having a matrix, a design matrix phi that is centered, it turns out that A transpose times this vector of 1s is also equal to 0. Okay? I am not going to go term by term, but if you take A transpose to be the transpose of this vector times this vector of 1s, you can see that every single term disappears. So the only thing you're left is A transpose A that looks like this. And now notice something interesting. There is no mu0 anywhere, right? There is no W0 anywhere. And this equation almost looks like our original, quadratic term in our likelihood model with this W not having any bias terms on it, and we can make this to look exactly like our original problem by centering our target values t. So here's the idea. You center t, so this t that you see in the equation below, it's really t minus the average of t's times a vector of 1s, and then you look at this problem, and this problem, it's exactly our original likelihood, which will lead directly to our well-known least squares problem. The only difference is this t that you see in the equation on the bottom, it's a center t. We have subtracted the average of the target values, and this matrix phi does not involve the bias term, and it is also a center design matrix. So bottom line, you can solve this problem using exactly the previous equations, knowing what t is and what phi bar is, and once you do that, you can actually go back and compute the estimate for W0 or mu from the equation that I gave you before, that effectively tells you that the bias term is the discrepancy between the average target and the average prediction using average basis functions evaluated over all your training data points. Okay, so that's it basically. So what you need to do in this type of problems is form a design matrix that does not involve the bias term, subtract from each column the average, okay, center also your target values, solve this least squares problem with your usual least squares equations, the normal equations as we call them, for finding all the W's except W0, and when you're done, you can go back and compute from this equation on the bottom what W0 is all about. And I think I am giving you a trivial example, actually, an application of this. Somehow, maybe you should have liked to have this trivial example first and then the general case, but things are the way they are in my slides. So we have a simple regression function, and you notice the bias term here has been pulled out, so this W has no bias term. It directly multiplies x. There is no phi of x here, so my design matrix capital phi is actually a matrix that I can denote as capital X, okay? So you can compute W0, as we said, separately if somehow you can evaluate before what W is, all right? So in this particular case, W0 is nothing else but the discrepancy between your average target in your training data and the average response of your regression function using your average X in your training data. So this is X bar and T bar, exactly as we said before. And the question is, how do you compute W? You're going to solve your regular least squares problem, and I'm just going to go and directly give you what the answer is. Your regular least squares problem will be X transpose X inverse times X transpose times your target values. You notice here I instead of denoting my design matrix as capital X, and by the way, I don't use capital phi because there are no basis functions. I work in the original space. All right, so phi has become capital X, but you notice I put a subscript XC here to remind you that this is a centered, design matrix, which effectively means that I have subtracted from every column of that design matrix, I have subtracted the mean component, okay? And you can see I have done the same thing with the targets. From every target value Ti, I subtracted the mean value. And here is what the centered X matrix looks like, okay? So from the first column, you subtract the average of the values in the first column, you subtract X2 bar in the second column, etc. You do the same thing with T bar. That's your regular least squares problem. So you already have computed what the least square solution for W is. And once you have W, you can come back to this equation and compute what the bias term is going to be about. So what you need to do, and you can actually do it mechanically once you understand the mechanisms of what I discussed here, is take your design matrix without the bias term, center the design matrix, solve a regular least squares problem using the design matrix, but also by centering your target values. And once you're done, come back and compute what the estimate of the bias term is. And I think that will be the nice pre-processing to do on this problem. And I think similar ideas will be applied to many other machine tasks as you can anticipate. Okay. So that's all for now, and I think we are ready with the next lecture to actually move to the fully Bayesian setting for regression. So one of the first things we will do is introduce a prior model on the parameters W, compute the posterior, see that map estimate of that posterior, it actually gives us ridge regression, and then from there proceed to come up with a complete posterior model for regression and a complete predictive distribution that uses that posterior. So there will be lots of fun and lots of interesting things to see in the next lecture or so. So until then, good readings. Bye.